Let's continue. So now that was a bit of detour, but to show that indeed the baryon number and winding number are actually the same thing. And now we are going to see, just by doing the quantization of this theory, that indeed the baryon, the soliton that we find are all the properties of proton and neutron. Okay, and the first thing we can ask is, what is the spin of our soliton when we quantize it? And I mean, to see this, the obvious answer would be, okay, we have a theory of mesons. So we put mesons together, it's a bounded of mesons. It's only spin 0 that we have in our theory. So how could this be not spin 0? But actually it's not totally true, because when we write down this Westermino-Witten term, there is some kind of hidden things that remembers that the underlying theory is the theory of fermions. Indeed, if we were looking only at this theory, this purely bosonic without the Westermino-Witten term, then the soliton would be a boson. But okay, so how do we compute the spin of the Skyrmion? So let's compare two processes. One where we take our soliton and we let it stay there in time, basically. Over a long time, the soliton is doing nothing. It's sitting at the point. So what is the amplitude for this process? So we know the soliton, when static, all the time derivative vanishes, and the Lagrange is just going to give us minus the mass. So if you want the action for a soliton that is totally static and is doing nothing is just the mass, and then let's say over a long time, let's say the amplitude of the process of baryon staying there, Skyrmion staying there and doing nothing, is just the exponential of minus I, and then the Lagrange just gives the m, what I call the mass of the soliton, which is just the energy of the soliton, which we call then 0 as that, times the time the baryon, the Skyrmion is staying there. This is the amplitude for just a Skyrmion sitting there over a long time. And now we want to compare this amplitude to the amplitude of a Skyrmion that we take and that we slowly rotate by 2 pi. Basically, we do a complete rotation and we come back, the full object, right? And we want to compare those two amplitudes. And when we rotate very slowly over a long time our soliton, what we'll get, the amplitude, this is for static. And then for slowly rotating, the amplitude is going to be exponential of I. And then we have the same part that is, if you want, that is the static part. But there will be a part that has covered that depends on the velocity at which the Skyrmion is rotating. But from this Lagrangian, you see that we have always two time derivatives at least. I mean, it's either the terms that have 0 or terms that have 2. So those are of like velocity squared, if you want. Since we do an adiabatic transformation very slow, this is subleading. And subleading with respect to what? With respect to the Westermino-Witten term. The Westermino-Witten term has the epsilon tensor, mu sigma. So it has exactly one index that is time, and then 4 derivatives. So it has exactly one time derivative. So in the limit where you take the soliton and you really rotate it slowly, it's the West-Witten term that will get the leading time dependence. And then it's yeah, we have to find a way. There is a way to parameterize this, which is easy, is to say, okay, we take our field U. This was U0 was our static solution here, and we say, okay, let's take a field of U of space and time, and we make just a rotation in space which is equivalent. We saw last time if I rotate this xi is the same as if I do a SU2 transformation. So I'll just do IT sigma 3 over 2 times U0 exponential minus IT sigma 3 over 2. I just pick the direction in the SU2 space basically, and I do a rotation of this. And then I take t, yeah, going from 0 to 2 pi over a long time. Okay. And then what we want to do is compute the value of the Witten term. And this is something that is a 5-dimensional integral. So I need now to pick any 5D space that has the boundary being the 4D, and that gives me this on the boundary if you want. And this can be done actually. So again, we need to go actually to SUN bigger than 3. So how does this work? Is that here we take 3 generators that form a SU2 subgroup of this thing, but it's at the end it's the same thing. So it's not very important. But so Witten did this and found a way. Just you find one example that is doing this, and you compute what is the value of the Witten term. And the paper is very simple and very nicely written, but I will not go into it because it's a bit complicated to do the computation. But basically, for this, you find that gamma, when you integrate over the 5-dimensional space, meaning over full space, over time between 0 and capital T, the time we want to do, so over a long time, and over the 5th dimension, that is an arbitrary thing. When you do this integral, you find that gamma is actually equal to pi for this soliton that rotates by 2 pi. Okay, and what does it mean? So it means that here our amplitude, instead of being given by only the rest energy times the time, there will be a part now that is the coefficient of the Witten term, that is just the number of colors we saw of the underlying theory, times pi. And this thing is just minus 1 to the power nc times the same exponential as it does before. And yes, if you want, there would be additional time dependence, but that is going to be subleading. So in the diabatic approximation, the amplitude of a soliton of a skyrmion staying there over time, and the amplitude of a skyrmion being very slowly rotated by 2 pi, differs by this factor of minus 1 to the power nc. And what does it mean? It means actually that if nc is even, it's the same thing. If nc is odd, it means that rotating the soliton by 2 pi, you gain a phase in the action, a minus 1 phase. So it means basically that the soliton is a Fermion. And yeah, this is the way.
Why does it mean so that then?
Because the spin, I mean, it gives you the spin if you want of the field, right? So spin 1/2 is a spin 1/2 particle is a particle that when you rotate by a factor of 2 pi, you get a phase in a minus 1 phase in the action, no? While
But are you rotating in group space? Here you're rotating in group space, not in...
Yes, okay. But this is a similar way. I could rewrite this if you want as a rotation over... no, but a rotation over this coordinate is the same as doing a rotation on the SU. I can do the same thing. This is exactly equal to saying I do some rotation, some time-dependent rotation of the coordinate x. And yeah, exactly, u0 of this. I can rewrite this exactly this way. So it's really a rotation in physical, sorry, physical space. But then you see directly that the same thing applies to isospin, basically. Is that yeah, you get the same. Yeah, the same phase if you want from the isospin transformation over. But okay, the interpretation of this is not clear to me. But doing a physical rotation of the object, you get of the 2π rotation of the object, you get a factor -1 in the action. So this is the rule that say that because of this Westermino-Witten term that is there with coefficient nc, you get this phase -1 to the power nc. And this is a paper of 1983 by Witten. I mean, there's two papers, both of them in one after the other. The first was to say that indeed the coefficient of the Westermino-Witten term has to be the number of colors. This is the first paper. And the second paper is to say that then the Skyrmions that are there are fermions in the case of.
Could you remind me why do we need the Westermino-Witten term there in the quantum theory and not the classical theory?
Well, so if you want, this is still at the semi-classical level, right? But we need it because we know that the underlying theory. We know what the underlying theory is. If you want. We need it because. So if you don't know what the theory is, you don't know. In principle, you don't know what the NC is. So there is a factor of the Westermino-Witten term that could even be 0. You can have no Westermino-Witten term in principle. If the underlying theory is a bosonic theory also, no anomalies, you don't need the Westermino-Witten term. But in QCD we know the theory of quarks, so we know that this coefficient is NC, and we get this. So the Skyrmion in QCD, it's the important one. Is in QCD the Skyrmion is a spin 1/2. Is a fermion. In other theories, you can have a Skyrmion that is a spin 0.
So, but the answer to Espen is because we have an anomaly in QCD.
Yes.
We need this,
yeah, exactly.
Okay, so
but you can have a theory that has an anomaly.
That
has an anomaly. If QCD had 4 color, the Skyrmion would be a spin 0.
Sure,
yeah, but you would need this
so
Westermino.
Yeah, you would need the Westermino. So you need it exactly to match the anomaly.
So
and whatever it is.
If pions were fundamental objects, then we would not have a Westermino.
Yeah, exactly. But depending on this coefficient of this term, which can be 0 or non-zero or whatever, this fixes the spin of the Skyrmion in this way.
So it's a sort of link between QCD and the effects of pion theory.
Yes, the Westermino-Witten term is really like is encoding all what remains of QCD. So not adding no physics if you want, no equation of motion. Well, okay. Nearly no physics to the thing, but encodes all the rest of QCD. If you want. But yeah, so at this level of Skyrmions, it's very crucial because the rule is if NC is odd, the Skyrmion is a fermion. If NC is even, the Skyrmion is a boson. But
sure. And then it makes perfect sense that the Skyrmions would be dominated by the Westermino-Witten term because they're not really Masonic objects.
They're not
Masonic objects. So of course they would be dominated by the pion theory, which is not actually Masonic.
Yeah. Sure.
If NC is odd.
No, it's still if NC is even, the Westermino-Witten term.
It just happens, if NC is even, it just happens that this contribution is 0 because it's 2π basically.
Oh yeah, sure, in this particular context.
Yeah, exactly.
But I mean, other Skyrmion properties would still be dominated by it, right?
Well, it depends, because for the mass is, for instance, the Westomino-Witten term. This is another thing I didn't say, but when you plug this thing in, is zero. So it doesn't give a contribution to the mass, to the moment of inertia of your object, if you want, to anything. But then the quantum properties are mostly determined by the Westomino-Witten term. If you want, one way of seeing it is, yeah, the classical properties are all fixed, but which is surprising, because you could say everything is determined by the Westomino-Witten term would be somehow no surprise, but that the theory of mesons is fixing the mass and these other properties. It's quite surprising to me. Yeah. So yes, and then there is another little side note that I have to say is that there is a problem for if you take SU2, because if you take SU2, there is no Westomino-Witten term. So in principle, if you take SU2 theory, you could think that Skyrmions is automatically a boson. But this is not true. From another reason is that SU2 actually has the fourth homotopy group of SU2 is non-zero. Is actually a Z2. And the fourth homotopy group of any SUN bigger than 3 is 0.
Is this related to this thing about Francesco like to say that SU2 is really SP2?
Actually, yes, maybe. It's probably what Francesco means. Although I'm not sure what the fourth homotopy of SP2 is. I have this here, so of SPN, because I think it's also 0. I think it's just SU2 that is very special. Let me just check this thing. It's all there somewhere. No, I don't find it now. It's in the table. Yes, here it is.
Just Google for it.
It's 0. I'm not sure that Google gives you the World Cup directly, but the homotopy group. I'm not sure.
Of ordinary groups.
No, but so what this means basically is that so this is the maps of 4-dimensional space-time to the field. This means that it's trivial, so there is only one map from space-time to your field. While here there is a Z2, so basically it means that there is it's actually a bit pathological, this thing, because it means that your path integral is basically you're integrating over a disconnected set. No, I mean your field is always doubled value. No, you have for each point in space-time, you can be in two different. You've two different classes of space-time field configuration that are in two different topological classes. And you might this old paper by Finkelstein and Rubinstein that says that basically depending on how you treat this thing, I don't know how it works on the lattice, but this must be somehow a problem on the lattice, because the theory, until you say how you treat these two different topologically distinct classes, the theory is not defined. I mean, you have two different theories in principle by just saying that these SU2.
What are these topological objects? They are monopoles?
It's nothing. Well, if you want this, it means that there is here the theta vacuum, if you want, of the mesonic theory is trivial. Here it's not trivial. So you have two topologically distinct. You don't have instanton because you don't have gauge fields to go from one to the other, but it would be some kind of similar to instanton, but you don't have the gauge field to interpolate from one to the other. So there are no new objects, but you have to define how your theory is specify how your theory is defined actually. Yeah. And there are two ways. This is what they say. Basically, either you say that that the two vacua have the same weight, or if they have opposite, +1 and -1. And if they're the same weight, this Skyrmion is going to be a boson, and if you have opposite, it's going to be a fermion. So in principle, you have the choice. When you write down this SU2 theory, you don't have a Westomin-Witten term, but you have the choice. When you define your path integral, in principle, you have the choice to pick the theory where the Skyrmion is a fermion or is a boson. And to my knowledge, is the only difference that you will get in the theory.
But on the lattice, we do the fundamental theory.
Yes.
We do the QCD, if you want, with SU2 gauge group. So I'm not sure this is relevant.
And then I don't know, to be honest, I don't know how it works, because
with 2 flavors.
With 2 flavors.
I mean, certainly this interpretation of the Skyrmion as the baryon breaks down, right? Because in SU2, the baryon and the methane would be the same, wouldn't it?
SU2. Yeah. No, it's SU2 flavor, so the color can still be
SU3 flavor.
So it can still be made of three. I think it's SU2 flavor. So you only take the up and the down quark, basically.
Exactly.
So the gauge group stays the same.
Ooh.
But the point is, the Skyrmion, when you only take the up and down quark, it becomes a bit different. It's something, by only looking at the low energy theory, you don't know actually how you have to quantize it. That's if you want the short way. While as soon as you have SU3 or whatever, it's totally fixed by the theory.
Yeah. I mean, then you know it from sort of scaling down your SU3 theory.
Yeah, exactly.
But I mean, that's a bit of a cheat.
It's a bit of a cheat, yes. It's not, I don't know. I don't know if there is something fundamentally different on the lattice, for instance.
On the lattice,
between the
SU3 with
2 flavor and 3 flavor.
But I mean, what would the Skyrmion, as far as I can tell, that's something that goes out of the effective theory.
Yes.
So it doesn't really make sense to talk about Skyrmion of the fundamental theory.
No, exactly. No, there is no Skyrmion of the fundamental theory.
And then we are in Euclidean time.
Yes, the lattice. No, it's sure. But there is no Skyrmion in lattice because it's. But I don't know if there is a difference for 2 flavor form a 2 flavor QCD and 3 flavor QCD on the lattice. Do you know if there is any difference?
What do you mean?
At the level of the baryons, for instance, there is no. I mean, the properties of the baryons have been. In principle, they should be not. I mean, it's just, if you want, it's a problem of the effective theory. That writing down the effective theory in the 2 flavor case as this kind of specificity that you cannot write down the Westomin-Witten term. But okay, it's really a detail, and yes. But it's just a way of saying, even in a case where you have no Westomin-Witten term, in principle, you could have quantized the soliton as a fermion. Good. So now, let me do in a very short time the quantization itself. And what does it mean? We have a theory. I mean, so far everything is semi-classical or classical. So now what we want to do is say we have a theory. We have the vacuum state in our topological system, which is the baryon. I mean, it's not a vacuum, but we are in a topological sector where we have a baryon that is localized in space, and we want to quantize around this. And what we want to do is just know what are the lowest energy properties of these things. So we don't need to do full quantization on non-constant background, because this is also something I don't know how to do. But we can do what is called a zero-mode quantization, or also collective coordinate quantization, which is basically to say we have our Skyrmion that is defined like this, and these are the number of symmetry that are not modifying the energy. So basically, these are the zero mode. And what are the zero modes here? One of them is translation, because basically you can locate your Skyrmion anywhere. You could always replace the x by x minus some other thing. The other symmetry is a rotation. A rotation of this will not affect the energy. And the third symmetry that there is SUN transformation, basically. But the rotation and the SUN transformation are actually the same thing. I mean, the rotation is a group of SO3 subset of the SUN transformation that you can do. So what do we do? Is actually we say that okay, we add coordinates that are going to be collective coordinates. So theta I that depend on time, and we allow the Skyrmion to rotate basically. So we say it's a bit the same as what we did before. Is we take a configuration U of x and t that is just some SUN rotation of the U0 configuration that we have here, A dagger. Okay, and A of t, we can write it is some SUN matrix. So let's now go to SU2 again because it's the simplest. You can just write it as with this Euler angle. So now I have so I have three angles that parameterize my SUN matrix, and I just write it in this way. It's one parameterization that makes it a little bit easier. And then I just plug in this new field into this Lagrangian, and what I get basically is that the Lagrangian is going to be, oh sorry, actually not the Lagrangian, but let me write the action, is minus the energy of the zero of the static field plus 1/2 something I call lambda, and then there is the theta I square is to theta dot, which is dot, so which means prime derivative theta and theta 3, 1 theta 3 plus theta 2. Where this n0 we saw what it was last time, and the lambda is another integral to 3 1/5 e cube, and then the integral of 0 to infinity r squared sin theta square of the function f, and so on plus f prime square. Sorry, yes. Oh, it's totally irrelevant, but it's there. And when you plug in the function f, you get a number that is 53.4 over 1 over f5 e n e cube. And this is basically the momentum of inertia of your theory. So we went from, we cannot quantize this full quantum field theory because it's too complicated. So what we do is we say, okay, we have our Skyrmion somewhere. Forget about the translation because this will give the quantization of the momentum of the object. So it's not very interesting. But we quantize the rotation basically, and rotation or a SUN transformation of this object. And this gives me an action that is written in terms of this coordinate theta 1, 2, and 3. Where and m and lambda are just number. M was 72 something for e. And then I do the quantization of this thing. So the usual thing, writing the Hamiltonian from this, using the conjugate the canonical momenta, and then replace the momenta by derivative. And then the point is I get to a Hamiltonian that is a bit complicated, but can be written very simply. I get this Hamiltonian, which is just m0, this number plus some operator, which is actually the Laplacian over 2 lambda. The Laplacian over 3 sphere.
But why do you want to do this? Can't you just use Feynman path integral quantization?
Yeah, but
So-
you're in a background, you're in a field that is not a vacuum. This is the difficulty. If you can't do this,
And you cannot do it then.
no, I don't think so. I don't think so. Well, I don't know. This is the quantization that is usually done. This thing. Because the zero mode at low energy, the only important thing. I mean, it's not true. Actually, what people do also is sometimes add other collective coordinates that can also parameterize the radial mode of the Skyrmion, but things get much more complicated, and the lowest energy states are the same. Which this thing looks at this point looks a bit, if you want, disconnected to the reality. But yeah, let me just. The thing is, then we can express the spin and the isospin in terms of these variables, and we will cover the same thing. And theta is just the Laplacian on a free sphere, which is a complicated differential operator in terms of these theta here. I will not write because otherwise we still need to more. And the eigenfunction of this thing basically are the Wigner d functions with this d, j, and prime of theta, and the eigenvalues are n0 plus, and then it's j times j plus 1. It's just the eigenvalue of the angular momentum operator, if you want this. This is going to be the physical energy of the various states. This is not telling us very much, but what we can do basically is compute from this the spin and the isospin of our Skyrmions in terms of this collective coordinate. And yes. And yeah, what we would get for the spin and isospin, let me just write. So the isospin operator is just we get I lambda place of A 0 A dagger, or A is this A that I took up there, times some generator TK, and the spin operator is nearly the same thing. A dagger 0 A TK. I could write it in terms of the theta variables, but it's not very useful. The point is that these operators I and j are related by a rotation, basically. Where R is another thing that we can compute in the theory, which is trace of TK A. And the important thing is that we get that the isospin square is equal to the isospin square operator is equal to the spin square operator. So what is the physical state, as I was saying, that are represented by this wave function? Basically, they are states that have the same that have the same total spin and isospin operator, and that are the third component of the spin and isospin that are not the same, that differ because they're not the same operator. So basically, yeah, in terms of if it's a boson, not in QCD, but in different theory odd and even number of colors. The lowest energy state is the state that has the J equals 0. And then it has also M and M prime 0, because these M and M prime go from minus J to plus J. And it has a mass M0. If it's a fermion, like it's the case in QCD, that's a bit more interesting, because we have a number of we have a spin 1/2, and then they have a plus minus 1/2, plus minus 1/2 of isospin and spin, third component of isospin and spin, and the same with the exactly. That's it. So we get actually 4. They generate 4 fermions with mass M0 plus, and then it's 1/2 plus 3/2, 3/4, 3/8 lambda.
What is lambda again?
Lambda is just is a number actually that we get from this thing. It's basically the moment of inertia of the Skyrmion.
And the estimate is what?
Is 50. Is the same order of magnitude as M0 in different units, inverted unit. So this is, if you want, is 72 f pi over e, and this is plus, but it's small because it's 1 over 50, and then it's f pi times e cubed. So in unit of f pi, you see if e is of order 1, this thing is actually negligible. So the mass of the Skyrmion is still given by mostly by this thing.
So lambda is large.
Lambda is large, actually. That's true. But what is interesting is then also the physical thing. The third component of the isospin, computed in this way, you can check that.
But sorry, should I think of this as an expansion and there are order 1 over lambda square and so on?
Actually not. It's an expansion.
Well, if I have more operators there or something, can they keep...
Well, the thing is, in general, you should have a full time dependence of the field. This is how you should quantize the most general thing.
Mm-hmm.
But
you
okay, yeah, no, it's true. You can see it as an expansion.
Sorry, but what you quantize is that action there, right?
Yes.
So if you had more operators, would you get terms 1 over lambda?
In this action?
What you are trying to quantize is that.
Yes, right? Yes.
Suppose in that action you had operators with more derivatives.
Yes. More than...
Higher orders, more than the
yes.
4 you had. So e to the 6. Then would you get 1 over lambda square terms? Yeah.
I would get different numbers for here and for here. But I would not get 1 over lambda square doing this collective coordinate quantization. I'm not exactly sure how this expansion works there. But, well, okay, let me go to maybe the final thing I should say, because we're running a bit late. Is that, okay, so the third component of the isospin, from this you can see that actually, if you plug the thing in, this theta, you get 1 over 2, actually, d theta 1, I think. Okay, the important thing is that the action of this on a state, on this state here, for instance, is just given me m times the same state. So basically, is an object that. Okay, see. The isospin, so our boson, if the Skyrmion is a boson, it has isospin 0. If it's a fermion, our Our Skyrmion has isospin plus or minus 1. Okay, so this is the difference. If it's a boson, it's a scalar, and there is only one of them. That is scalar with one real scalar, if you want. If it's a fermion, we get fermions with isospin plus or minus 1/2. I mean isospin, total isospin. Yeah, exactly. And then the last thing maybe is is what about the hypercharge of this thing? Because the isospin actually we could expect it, but the hypercharge, as we were discussing, gauging the electromagnetism, was all about saying if we had with this generator that was in the two-flavor case, this isospin generator, that is this I3 I wrote before, jump, plus, and then in the case of QCD it was plus 1/6 times the identity. But let me put here plus 1 over NC in general. I could have anything here.
1 over NC?
Yes, I choose this because this was what was giving me the pi 0 to gamma gamma as I wanted. But in principle, this is a free. Let me put a y here. I divide by NC for a reason that you will see.
Sure.
Right now.
It was the diagram of a factor of 2.
Exactly. There is always a factor of 2 wrong in all things you can compute. But the point is, if you plug if you compute what is the conserved neutral charge associated with this hypercharge transformation, basically. So now I split the isospin, I have computed it, and the hypercharge is like this. You see that you get nothing, because this is the identity, so in the covariant derivatives it's totally disappearing, right? It doesn't care at all about the hypercharge thing. But we get from the Weston-Minor-Witten term, we get what we were getting before, which is actually independent in this case of these theta coordinates. So we get basically that the hypercharge operator on this Skyrmion is just, in this case, the coefficient of the Weston-Minor-Witten term, that is NC, times this hypercharge thing, which is what we call small y over 2NC, right? This is why I put a 1 over NC here, because then I can cancel the NC. And in QCD, so you see in QCD, maybe I should not do this. Keep it simple. Good. So this thing, the hypercharge is just 1/2. So what are the electric charge of our fundamental state? Is 1/2 of isospin, plus or minus 1/2 of isospin plus 1/2 of hypercharge. So basically, if the Skyrmion is a fermion and the hypercharge is implemented like in QCD, then we get this Skyrmion of charge plus 1 and the Skyrmion of charge 0 that correspond exactly to the proton and the neutron. While if you do the same thing now with the, and you see that you can get this for any NC odd. So actually, for NC being 5, for instance, you would get get the same thing that you get the proton and neutron with charge plus 1 and charge 0. I mean, there is no, from this point of view, we can get all mesonic and baryonic physics without knowing what is NC. If NC is even, then it's a bit different, because if NC is even, there is no isospin, so the electric charge of the Skyrmion is given by this hypercharge, and then depends what you pick here. So yeah. Okay, it's always even what you pick here. But so it's just to say that this matches exactly the picture that.
So how does the I'm sorry to interrupt. How does the anti-proton get its charge? So you have 4 fermion states, which I guess you identify No, never mind.
Yeah.
I'm being an idiot. No, man.
You get the. I mean, if you want, you can always.
You never
take the one in number minus one thing, and you revert all of what I said. Actually, the hypercharge, you get minus the hypercharge. So you'll always get soliton and anti-soliton.
Yeah, sure. I was just being an idiot when I saw the 4 fermions.
So the bottom line, if you want, is that everything is exactly in agreement with. So you have this theory of mesons, but the Skyrmions that you get exactly have the quantum number of an object that is made not of mesons, but that is made out of NC objects, if you want, with some hypercharge that was given. So in QCD there would be only 3, so we have 3 objects with hypercharge 1/6, so you get hypercharge 1/2, and then you get the spin and isospin. The interesting thing is the lowest mass objects of all these Skyrmions that you get are the one that have the lowest spin and isospin, which is but that have a spin or isospin 1/2. So basically means that you have this half of the objects of spin isospin up, if you want, and half of spin isospin down. And the lightest excited state, if NC is even, you will get a spin 0 out of this, the lightest state. If NC is odd, you cannot get a spin 0, so you get 2, you get spin 1/2 and spin -1/2. But it's not trivial that you get this to be I mean, it's not trivial. All of this is trivial in the quark picture, right? But it's not trivial at all in the meson Lagrangian picture that you get this thing, right? Yes. Okay, there are a number of things we could talk about, and but I won't do it now. And if you have questions, I mean, the last thing I can say is that maybe I should say is what I was saying before, is that this winding number integral is not gauge invariant. If you decide to gauge the symmetries, there is no gauge invariant quantity that tells you what is the winding number of a field configuration. But you can define a quantity that is gauge invariant, and that is basically the winding number of the soliton plus the Chern-Simons numbers of the gauge field. I mean, actually, if you have only a vector gauge field, so you only gauge the part that is unbroken of this, then the baryon numbers, the winding number remains is actually gauge invariant. If you gauge the axial part of this thing, the part that is broken, it will get a mass from the vacuum expectation value of the field U. Then you need indeed the quantity that is gauge invariant is not the baryon number, but is B plus the Chern-Simons number of the gauge field, plus minus B squared over 16 pi square, and then there is this Chern-Simons number, which is the this of the gauge field or something. Well, actually, this normalization is because this is the thing that gives you 1 or 0. So basically, what happens when you gauge in the presence of a gauge field that is not vector-like, so actually exactly like the electroweak field in QCD, because it's something that is broken by the I mean, the W would get a mass even if there was no Higgs, actually from the baryons, right, from the breaking of chiral symmetry. So in this case, there is no winding number that is a gauge invariant quantity, but there is linear combination of the winding number and the Chern-Simons number of the gauge field. So what happens if you take what is a Skyrmion in the presence of gauge field, it's the same thing by doing a gauge transformation, which might be singular or not, depending on how it is. It's the same as a pure gauge configuration, which is not something very interesting. But the point is, if you have a skyrmion and a trivial gauge configuration, and you want to evolve these into no skyrmions and a trivial gauge configuration, is what you can do is having a skyrmion and a trivial gauge configuration is saying like having a non-trivial gauge configuration, and this can tunnel with an instanton to a trivial gauge configuration. So basically, when you have like in the standard model, when you have some gauge fields that are broken by this linear Lagrangian, you can have the skyrmion can decay, and it can decay through an instanton. But this is a thing which has a probability that is, so an amplitude, if you want, that is exponential of 8 pi square over g squared, something like this. So it's a process that happens if you compute from this. You see in the standard model that you have skyrmion decay, but the decay time is much longer than the age of the universe, and which is basically what you get in QCD. The baryon number is not protected, so the baryon decays in the standard model, but the decay time is at low temperature, at least, is zero temperature is extremely high, is extremely long, the decay time. But at high temperature you have the spiral process, and then it's a different story. Yes, let me cut it here, and see the interesting thing is which was basically my PhD thesis was to try to apply this to
be modest
to the. I'd say it was good. I'd say it was interesting.
I've done before was not
but it was not. I was not the first, and it was not my idea either. It was my idea. But is to try to apply this to technicolor models and compositics models, because basically you have the same thing. You have description in terms of meson theory of the electronic physics, and the question was to ask: are they baryons? Are they skyrmions? And then depends. They can even be a boson, and if it's a boson that has zero charge, it will be the optimal dark matter guy. So a guy that has no isospin, that has no spin, just totally stable by topological property. But okay. Point is, it doesn't work in most of the models, either because there are no skyrmions, depending on the topology, or because then the hypercharge. One interesting conclusion was that the hypercharge assignment that some people do in some model would give skyrmions that have an electric charge. Those models don't have a UV completion, so you cannot even check on the lattice or something like this. If indeed there is a stable object with an electric charge or something like this, but generally is not the thing you would like to have too much around in a model, a heavy particle with an electric charge, unless you have some mechanism to kill it, to make it decay fast, but generally it's not possible. Okay, let me stop here and we can have a discussion also around the beer. Good.
Thanks, Mark.
Okay.